If you want to know every aspect of quantum teleportation, you've clicked on the right video. What if information could jump from one place to another instantly without moving through the space in between? You'll learn what's really being teleported, how it happens without faster-than-light travel, and what this tells us about the nature of reality, quantum computing, and future technologies. Teleportation is one of the most fascinating ideas in science. At its most basic level, teleportation means moving something from one place to another without crossing the space in between. Teleportation, as scientists understand it, is about sending the exact state or information of a particle from one location to another without physically moving the particle itself. This is called quantum teleportation, and it's something scientists have actually done. Quantum teleportation is possible because of a strange but real feature of the universe called quantum entanglement. To understand this, we need to look at how particles behave in quantum physics. In the quantum world, particles like electrons and photons don't behave the way things do in our everyday world. They can exist in more than one state at a time. They can be connected to each other in a way that seems impossible. When two particles are entangled, whatever happens to one instantly affects the other, even if they are far apart. This is not just a theory. It's something scientists have tested many times in laboratories. In quantum teleportation, entangled particles are the key. Imagine you have two particles, particle A and particle B, and they are entangled. Particle A is in lab 1 and particle B is in lab 2. You want to teleport the state of particle A to particle B. You do this by performing a special kind of measurement on particle A. When you do that, particle B, even though it's far away, instantly takes on the same state that particle A had. It's as if the state of particle A has been transferred to particle B, without anything physically moving between the two labs. This is quantum teleportation. The original particle doesn't move, but its exact state is recreated in another place. This might sound like magic, but it's real science. Quantum teleportation has been done many times using particles like photons, electrons, and atoms. In fact, scientists have even teleported quantum states between particles over long distances, between cities, and even between the ground and satellites in space. These experiments are not just for fun. They are helping scientists build new kinds of communication systems that are more secure and faster than anything we've had before. In a way, quantum teleportation is showing us a new way to move information, not through wires or radio waves, but through the structure of space itself. One of the most advanced achievements in this field was made by scientists at the University of Oxford. They used a type of atom called a calcium ion and entangled two of these ions with extreme precision. These ions were trapped using electric fields and cooled down to near absolute zero so they would not move or vibrate. Lasers were used to control the ions and perform quantum logic operations. The scientists were able to teleport the quantum state of one ion to another with over 90% accuracy. This level of control is extremely difficult to achieve and shows how far quantum physics has come. The Oxford team's work is one of the clearest demonstrations that teleportation is real, at least at the level of atoms and quantum states. Teleportation of people or large objects is not something that science can do today. There are many challenges. For one thing, a human body is made of trillions of atoms. To teleport a person, you would have to know the exact state of every single atom in their body, including their brain, memories, and emotions. That's more information than we can store or process with today's technology. Also, quantum teleportation does not move the object itself. It only moves the information about its state. There was some public discussion about scientists teleporting a tardigrade, a microscopic animal known for its toughness. Tardigrades can survive in space, in boiling water, and even after being frozen for years. In 2021, researchers conducted an experiment where a tardigrade was placed near a superconducting quantum circuit. Some people believe this experiment involved teleportation of the tardigrade. However, the truth is that the experiment did not teleport the tardigrade. It was simply used to test whether a biological organism could be part of a quantum system or interact with quantum fields. The tardigrade was not teleported, and there is no scientific proof that any living organism has ever been teleported. Even though we can't teleport living beings, the work scientists are doing today is laying the foundation for what might be possible in the far future. Quantum teleportation is already helping us build new kinds of computers called quantum computers. that can solve problems regular computers can't. It's also helping us create quantum networks, which are a new way of connecting devices using the rules of quantum mechanics. These networks could allow people to send data instantly and securely using teleportation of quantum states instead of signals. Quantum teleportation has the potential to completely transform the future of communication by introducing a fundamentally new way of transmitting information. Unlike traditional communication methods, which rely on physical signals like electrical pulses through wires or electromagnetic waves through the air, quantum teleportation moves information without transmitting any particles or signals through space. Instead, it uses the principles of quantum entanglement to instantly transfer the state of one quantum system to another, no matter how far apart they are. This opens the door to a new kind of communication network that is not just faster, but also much more secure than anything we use today. One of the most exciting possibilities is the creation of a global quantum internet. This would be a worldwide network of quantum devices connected through quantum teleportation links. In such a system, data would not be sent as regular digital signals, but rather as quantum states teleported between entangled nodes. Because of the rules of quantum mechanics, this kind of data transfer would be immune to eavesdropping or interception. If someone tried to spy on the communication, the quantum state would be disturbed and both parties would know immediately. This is because quantum information cannot be copied or measured without changing it, a property known as the no-cloning theorem. This quantum-level security makes quantum teleportation extremely attractive for sensitive communication tasks. In banking, for example, financial transactions, passwords, and account data could be transmitted through teleportation links, ensuring that no hacker or third party could access them without being detected. In national security, quantum networks could be used to send confidential messages between government agencies, military units, and intelligence services without the risk of leaks or cyber attacks. Even in scientific research, where global teams often share sensitive or proprietary data, quantum teleportation could help protect discoveries and ensure that communication remains private and trustworthy. Additionally, a global quantum internet could also allow remote quantum computers to work together in real time. Researchers could teleport quantum information from one quantum processor to another, building larger and more powerful quantum systems across long distances. This could accelerate scientific discoveries, improve artificial intelligence, and allow advanced simulations in chemistry, physics, and climate modeling. Teleporting quantum information from one planet to another is an exciting and realistic possibility for the future of space exploration and interplanetary communication. While it may sound like science fiction, this idea is grounded in real scientific principles. Quantum teleportation does not move objects or people through space, but it transfers the exact quantum state of a particle from one location to another using the phenomenon of quantum entanglement. If entangled particles are shared between two distant locations, a measurement made on one can instantly influence the state of the other. This opens up the potential for instant, secure communication between Earth and other planets like the Moon or Mars. Currently, when we send signals from Earth to Mars, it takes several minutes for the message to arrive depending on the distance between the two planets in their orbits. This delay can make real-time communication difficult, especially for important tasks like controlling robots, managing life support systems, or responding to emergencies. But with quantum teleportation, there is a possibility to send quantum information instantly, although classical information still has to be transmitted. After a quantum measurement, the quantum part of the process happens without any time delay. This unique feature could drastically reduce waiting times and allow for quicker responses and decisions in space missions. To understand how scientists actually perform quantum teleportation in the laboratory, we need to take a closer look at the step-by-step process they use. It all begins with the creation of entangled particles. Entanglement is a unique quantum connection between two or more particles. When particles become entangled, they share information in a way that's not possible in classical physics. No matter how far apart they are, a change to one particle instantly affects the other. This is the key to teleportation. The first step is to generate two entangled particles, usually photons or ions. This is done using lasers and special crystals or atomic traps. For example, one common method is to shine a laser beam through a special crystal, which causes it to split a single photon into two entangled photons. These entangled photons are then sent to two different locations. Let's call them Alice and Bob, which are the names scientists often use in explanations. One of the most impressive achievements in quantum teleportation came from a team of scientists in China. They managed to teleport the quantum state of a photon from the ground to a satellite in orbit over 1,200 kilometers away. This was the first demonstration of long-distance quantum teleportation through open space. The experiment used a special satellite called Misconceptions, which was designed for quantum experiments. The ground station and the satellite shared entangled photons. When a measurement was performed on the ground, the satellite received the teleported state. This showed that quantum entanglement could survive the long journey through Earth's atmosphere and space, and that teleportation could work even across great distances. They managed to teleport the quantum state of a photon from the ground to a satellite in orbit, over 1,200 kilometers away. This was the first demonstration of long-distance quantum teleportation through open space. The experiment used a special satellite called Misconceptions, which was designed for quantum experiments. The ground station and the satellite shared entangled photons. When a measurement was performed on the ground, the satellite received the teleported state. This showed that quantum entanglement could survive the long journey through Earth's atmosphere and space, and that teleportation could work even across great distances. Another breakthrough came from the Delft University of Technology in the Netherlands. In 2014, scientists there were able to teleport the quantum state of an electron trapped in a diamond to another electron across a distance of 3 meters. While that distance is small, the precision of the experiment was a major step forward. It showed that quantum teleportation could be done reliably with solid-state systems, which are the kind of systems that could one day be used in quantum computers. One challenge in teleportation is maintaining entanglement over long distances. Entangled particles can lose their connection due to noise and interference from the environment. Scientists use something called quantum repeaters to extend the range. A quantum repeater works like a relay station. It refreshes the entanglement and helps keep the connection alive over large distances. These devices are still in development, but are critical for building quantum communication networks. Another challenge is fidelity. Fidelity is a measure of how close the teleported state is to the original. In perfect teleportation, the fidelity would be 100%, meaning no information is lost or changed. But in real experiments, there are always small errors. These errors can come from imperfect measurements, unstable environments, or faulty equipment. The goal of scientists is to reduce these errors as much as possible. In the Oxford experiment, the team reached a fidelity of over 90% when teleporting the state of a calcium ion. This is one of the highest levels of accuracy ever achieved and shows the potential for future improvements. Quantum teleportation also raises questions about the meaning of identity and reality. If you teleport the quantum state of one particle to another, is it the same particle? What happens to the original? In teleportation, the original particle is usually destroyed during the measurement. The information is gone from the first location and appears in the second. This is different from copying. In classical systems, you can make a copy of a file or an object without destroying the original, but in quantum systems, copying is not allowed. This is known as the no-cloning theorem, a fundamental rule in quantum physics. You can move information, but you can't duplicate it. Because of this, teleportation is not duplications. It is transfer. The original no longer exists. Only the teleported version remains. This makes teleportation different from what we see in science fiction movies. There is no glowing beam that carries your atoms through space. Instead, there is a transfer of your quantum information from one place to another. That's why teleportation is more about data than matter. Quantum computers are very different from regular computers. They use quantum bits or qubits, which can represent multiple values at once. Teleportation could be used to move qubits between different parts of a quantum computer or between different computers in a quantum network. This could help build more powerful and flexible systems. Some scientists are also exploring the idea of teleporting memory or information between quantum systems. While this is still a long way off, it raises interesting ideas about the future. Could we one day transfer our thoughts, memories, or even consciousness using teleportation? That's a question science cannot yet answer, but it shows how far the imagination can go when guided by real physics. One of the most important parts of any teleportation experiment is verifying that it worked. Scientists don't just press a button and hope. They carefully measure every part of the process. When a quantum state is teleported from one place to another, researchers compare the original state with the final result to see how accurate the teleportation was. This is done using precision detectors, which can analyze properties like spin, polarization, or energy levels of particles. The goal is to make sure the final particle truly matches the original down to every quantum detail. To make these comparisons, scientists often repeat the teleportation experiment many times. In a typical test, they might teleport hundreds or even thousands of particles and collect data for each one. This helps them build a statistical picture of how well the teleportation is working. The results are compared with theoretical models. If the results match the predictions, it means the teleportation was successful. If they don't, the scientists investigate what went wrong. Maybe there was a problem with the entanglement or the measurement or even environmental noise. As scientists gain more experience, they are trying to teleport more complex systems. The simplest experiments involve photons, which are particles of light. Photons are useful because they move fast and can travel long distances through fiber optic cables or even through space. But scientists have also worked with ions, atoms that have been given an electric charge. Ions are heavier and harder to move, but they can store quantum information more reliably for longer periods of time. In more advanced experiments, researchers are starting to combine different types of particles. For example, they might entangle a photon with an ion and then teleport a quantum state between them. This kind of cross-system teleportation is a major step forward because it could help link different parts of future quantum networks. One exciting area of research is chip-based teleportation. This means building tiny teleportation devices on small pieces of hardware like microchips. These chips can contain tiny optical circuits that guide photons along different paths using mirrors, lenses, and waveguides. By controlling how the photons move, scientists can create entanglement, perform quantum measurements, and carry out teleportation all on a single chip. This is important because if teleportation is ever going to be part of everyday technology, it will need to be small, fast, and easy to build. Chip-based systems bring teleportation one step closer to real-world use. Teleportation is also being tested in new environments. Most experiments started in labs under tightly controlled conditions, but now scientists are trying to teleport quantum states through real-world systems like fiber optic networks in cities. For example, in Switzerland, researchers have used the existing telecommunications network to teleport quantum information between buildings. In China, large-scale quantum communication projects have connected cities hundreds of kilometers apart using quantum teleportation. These experiments are not only about proving that teleportation works, but also about testing how it can be used in everyday life. Countries like the United States, China, and European Union nations are investing in quantum research for secure global communication. Challenges remain, including decoherence, loss of quantum data to the environment, and scalability, since current systems handle only a few particles. Scientists and expand quantum networks. Despite its challenges, quantum teleportation is rapidly advancing. Scientists are achieving better fidelity, longer distances, and greater control each year, much like early classical computers. Though people won't be teleported soon, this technology is already real and promising. It works by transferring quantum information instantly, though classical communication still obeys relativity. Potential applications span medicine, materials science, and artificial intelligence, where data could be securely transferred between labs or sensors. Teleportation is also vital for quantum computing, error correction, and a future quantum internet. While teleporting matter is far off, exploring it reshapes our understanding of space, identity, and the fabric of reality. Quantum teleportation is a global scientific effort involving universities, governments, and private labs, working together to build better entanglement sources, precise detectors, and stable quantum networks. These efforts are shaping the foundation of a future quantum internet. So what can we expect in the next 10 to 50 years? In the coming decades, quantum teleportation is expected to transform communication. Within 10 years, it may be used in major cities for secure data transfer in banking, healthcare, and government. As quantum repeaters improve, teleportation will reach greater distances. In 20 to 30 years, international quantum networks could enable ultra-secure global communication. By 40 to 50 years, teleportation might link satellites and space labs with Earth instantly. While human teleportation remains unlikely, this technology is real and rapidly advancing. It may also reveal deep connections between teleportation, black holes, and gravity, possibly helping unify quantum mechanics with general relativity at last. Quantum teleportation is not magic, it is science. But science, when explored with imagination and care, can sometimes feel like magic. That is the beauty of it. Teleportation is one of the most exciting frontiers in physics. Whether or not it ever moves people, it is already moving knowledge, moving technology, and moving the human story forward. The future is being built, one quantum bit at a time, and teleportation is helping to lead the way. Got something on your mind? Drop your questions in the comments. We'd love to hear what you're thinking. Thank you for joining us on this journey through quantum teleportation. Please like and share the video, and please do not forget to subscribe for more videos.